conference, and actually I've been here already for a couple of months, and I could appreciate the amount of mathematical activity that is done in this center, which is really outstanding. So let me start right away with the formulation of the problem that I'm going to talk about this morning. So we have isometric embeddings of or immersions. Riemannian manifolds in the Euclidean space. Okay, so our Riemannian manifold is given by sigma, the manifold, and a metric tensor G. So the Euclidean space is Rn, and so by this we mean simply that we have maps U, which are going from sigma into Rn, and the pullback of the Euclidean metric on the Rn, so this will denote the standard Euclidean metric, this is equal to G. Okay, so if you fix, so U is C1, and actually just the fact that this identity holds, it will tell you that the map is an immersion. Okay, so to be an embedding, it just means that it's injective. Okay, so actually in charts, this is equivalent to the following system of partial differential equations. So when I take the partial derivative in direction I of U, and I take the scalar product with the partial derivative in direction J of U, so this gives me the entry Gij of the symmetric tensor. Okay? So if you're an analyst like me, and you're using brutal coordinates, then you can actually even rewrite this in the following way. So you take the transpose of the matrix, which is giving you the derivative, the partial derivatives of U in the coordinates, and you multiply by U, and then you get G. Okay? So now, if you make a rough count over here, you have n times n plus 1 divided by 2 equations, and n unknowns. Okay, so therefore you would imagine that to solve this system of partial differential equations, you might need big N, at least bigger or equal than the number of equations that you have, right? So this is actually what you would say it's a reasonable guess. Okay, on the other hand, it was proved actually by Nash that as long as the topology does not give you obstructions for putting sigma into Rn, and as long as big N is bigger or equal than n plus 1, actually the system is solvable. Okay, so which is a pretty crazy statement actually. It's solvable in a situation in which the system is hugely overdetermined. Okay, so it's not yet on the web, and it has not yet appeared, but since I'm actually one of the editors, I could read Miller's comments on Nash life and mathematics. And so one of the things that he's saying is that this is what every reasonable person would actually expect, but this is what he writes down in his contribution. Nash was never a reasonable person. So in fact, the theorem that he proved, okay, so in this form, in fact, it's Kuiper. So if you want to be picky, Nash proved it for n plus 2. So n bigger or equal than n plus 2 is really Nash, and Kuiper is big N bigger or equal than n plus 1. But if you read carefully Nash's paper, he's just saying that n plus 2 can be done. It just does not want to bother to write down the details, because it's a bit more complicated. Okay, so let me actually give you the correct statement of the theorem. So the real theorem is the following. So if you start with a short map, and so here short map means that when I look at the pullback metric, I have the following inequality. So this is an inequality in the sense of quadratic form. So this just tells you that the map is actually shortening the length of curves. Okay, then for every epsilon bigger than 0 that exists in isometric embedding, such that v minus u in C0 is less or equal than epsilon. Okay, so now think about, for instance, the standard sphere. So of course a map which is taking the standard sphere and is shortening every curve so it's just making an homotopy and putting everything in a ball of radius epsilon is, of course, a short map. And then this theorem is telling you that nearby there is an actual isometry. Okay, so this means that actually you're able to crumple a standard sphere of size 1 into a very small ball in the Euclidean space, even in 3 dimensions, right? So this is very counterintuitive, and in fact, at the time, people believed that this could not be true. So you have to compare this to a classical problem, which is called the Weil problem. This would be a theorem which goes back at least to the 19th century. So it would be, for instance, Liebmann, but then there is the contribution of Cohn-Vossen and Herglotz. Okay, so if sigma is the standard sphere with a metric with positive Gauss curvature, and U from sigma into R3 is an isometric immersion, at least C2, so this actually will only be C1. Okay, then, in fact, U of sigma is unique, meaning, of course, that you can compose with rigid motions and you would get still an isometric immersion. But up to rigid motions, which are the obvious things which violate the uniqueness, actually the shape of the immersion is determined. In particular, for instance, the shape of the immersion would be a convex surface. Particular, U of sigma is convex. Now, there's a very trivial argument which is telling you that this one is never going to be convex. And the argument is the following. So, if you want to put a convex surface, of course, in a very small ball, then the diameter of this convex surface has to be sufficiently small, okay? The diameter is something that you can compute from the metric. So it's obvious that something like this cannot be convex in this situation, right? So since something like that cannot be convex, it's also obvious that this immersion is violating the so-called theorem egregium by Gauss that is telling you that the determinant of the second fundamental form equals the Gauss map. Okay, so Nash Kuiper's solution violates Gauss theorem egregium. Of course, you could ask, well, if you have only a C1 map, what do I understand by Gauss theorem egregium? Well, you can make a formulation of this, because if you have a C1 map, you have a very well-defined normal. The normal will be a C0 map, and you can interpret the Gauss curvature as the area distortion of this Gauss map, right? So actually what you can do, for instance, you can look at the area, which is, you take a portion of the manifold, you compose with the immersion, and then you compose with the Gauss map, and then you get a portion of the sphere. And then you can measure the area of the portion of the sphere, because this is going to be a very nice set. And you can see whether you can compute the area of this portion by using the integral of the Gauss map on the original set, okay? So of course you have to talk about signed area in this case, right? So because if the Gauss map, if the curvature is going to be negative, this means you're actually counting that area with a negative sign. Okay, so one way to make sense of this is, for instance, to write down a change of variables formula for the Gauss map. So one way would be to use degree theory. So I'm not going to explain this exactly, but there is a way to formulate Gauss theorem egregium. For C1 maps. Okay, so in fact, just one comment. If you look classically at the proof here, they will require 3 derivatives on the metric. In fact, C3 if you look at the classical proofs, but it's very easy to pass by approximation and prove it for C2. Okay, that's a simple exercise in calculus if you want.
What about
for a good student? Sorry?
Pocolero's uniqueness is much more tough.
Yeah, I'm going to talk about that actually. So this one is a result of the 20s. Okay, Pogorelov is much later, but I'm going to mention that actually in a second. Okay, so the question that I want to ask today is about a threshold between these two behaviors, between the rigidity behavior and the flexibility behavior. So what about if I look at C1 alpha surfaces? So ideally you would like to identify, or you would expect that there is a certain threshold alpha for which below this threshold you have a behavior like the Nash Kuiper theorem, and above this threshold you have a rigidity behavior. Or for instance, above this threshold you could say that Gauss theorem region works, which is already a sign that something more rigid is happening. Okay? So is there a threshold? Okay, so it might look as a peculiar question. So first of all, it's actually quote-unquote a classical question. So it certainly at least appears in Gromov's book on partial differential relations. And it appears also in Yao's collections of open problems in geometry. Secondly, and most importantly, there is a nice conjecture in the theory of turbulence where something similar is happening for the Euler equations. So this is a conjecture by a physicist, Lars Onsager, in 1949, and it's saying that for the Euler equations, for incompressible Euler equations, so there is a threshold alpha 0, and in some sense, C beta solutions for beta bigger than alpha 0 are good, and C beta solutions for beta less than alpha 0 might be bad. And this alpha 0 happens to be 1/3. And recently we could say that this conjecture is actually almost solved. So if you look at the way Onsager formulated the conjecture, actually the conjecture is still open. But in a certain sense, we can really say that there is this threshold 1/3, which is telling you how many derivatives you have to take to distinguish between a solution which behaves badly and a solution which behaves well. So modulo some lower order considerations, in some sense, on the number of derivatives, this conjecture has been recently solved, more or less.
By bad, you mean doesn't conserve energy, or what?
Yes, for instance. So that is actually the formulation of Onsager's. Yes. So above this threshold, it has to conserve energy, and below this threshold, energy might be dissipated. And if you want to know the difference between really solving the conjecture and not solving it, he's stating the conjecture really for Hölder solutions in space which have a uniform control on the constant. And we can prove the second part for solutions which are Hölder in space, but the Hölder constant in space is only L1 in time instead of being uniformly controlled. Okay? So if instead you want to stick to Onsager's conjecture, then what we can do is 1/5 instead of 1/3. So there is just a difference in exponent. Okay, so this problem over here was actually considered by a Russian mathematician in the 50s and 60s. So according to the stories that have been told by some other Russian mathematicians, actually he believed that he could prove rigidity for the Weil problem for C1. And of course, Nash was a counterexample to this. So he then turned to study C1 alpha, and for C1 alpha, essentially he had the following theorems. So C1 2/3 plus, say, epsilon 0 in the Weil problem. So, or somehow, let's say 2/3 plus, meaning just slightly more than 2/3 in the Weil problem, gives you rigidity. So he proved this in a series of 4 papers. And then he announced also the following theorem. So for sufficiently small alpha, and here alpha is depending on n, so the dimension of the manifold in this statement. The Nash Kuiper theorem is correct. The Nash Kuiper theorem holds. Okay, so this number alpha of n is actually an explicit number if there is no, if sigma is topologically a ball. Okay, so alpha of n is essentially, so if there is topology, there is more to work, and the thing becomes worse, but it's essentially the following number, 1 plus n times n plus 1. Okay, in particular, you see that for 2, it gives 7. Okay, so this, I say this is a theorem, but in fact, it's in 1963, and he announces this theorem. And he gave a proof in 2004 for the 2-dimensional case, but his alpha is 1/13, in fact, in the paper. So, in fact, the story goes that this was his habilitation thesis, but, he felt the theorem was not good enough, so he didn't want to somehow publish it. And then when he was very old, somehow his colleagues essentially forced him to publish. And then he published a version of the proof, which is kind of, in an easy situation, somehow not the complete proof, which would be more complicated. Okay, so anyway, in a subsequent...
which university?
Sorry? Where was he?
Where does he get his PhD?
So he was a student of Alexandrov, and he was in Novosibirsk as a professor. Anyway, so with Sergio Conti and Laszlo Zekelihidi in 2012, we have given a proof of this theorem. Say 2 by Borisov. Actually, better because in his assumptions, the metric G has to be real analytic, and in our assumption, G has to be C2. I will tell you in a second why actually the background metric for him here has to be real analytic. Okay, and we have given a shorter proof of theorem 1.
So current is still positive,
Yes. Here, yes, here. But here, no. I mean, this is going to be valid for any.
So up there,
Up there, yes. Bias problem.
Is non-negative good enough, or you need strictly positive?
No, you need strictly positive to make it work. So shorter proof for theorem 1. And shorter means 3 pages instead of 4 pages. Okay, and in fact...
Why do you need strictly positive?
Sorry?
Why do you need strictly positive?
Going to give you the argument in a couple of seconds. I mean, at least the idea. And in fact, if you have topology, this number becomes uglier, but it's still computable. So in fact, alpha of n could be equal to 1 divided by 1 plus n times n plus 1 squared if sigma is more complicated than just the standard. Okay, but most recently, and this is really the result I want to finally mention, So this is a joint work with Laszlo and a student, Dominic Inauen. So this is in 2015. So for n equal 2, you can improve alpha of 2 to 1 over 5. So, and this if sigma is a disk. Okay, and okay, how to go beyond this 1 over 5, we don't know. Okay, so let me give you a very brief sketch of the rigidity argument. So, and let me give you an idea why actually this threshold over here, 2/3, plays a role. In fact, I should mention somewhere that Gromov conjectures that the threshold is 1/2. And that's apparently what also Borisov believed, that 1/2 is the threshold. And that's the reason for this. Okay, so how the proof of this goes? Theorem 1. Okay, so remember that I told you that you want to show, I mean, one first instance of the rigidity is that if you could show Gauss theorem egregium, then there is a strong sign that you cannot do this construction by Nash and Kuiper. Okay? In fact, if you use the work of Pogorelov, it's almost direct. So if you can prove Gauss theorem egregium in the way I told you, with the distortion of the Gauss map, that will tell you when the curvature is positive that the image of your surface is a piece of a convex surface. And once you're actually convex, essentially you can start writing a PDE for the Weil problem. You can write Mogent there. Okay? So Pogorelov plus theorem egregium does the job. However, to apply this, you need strictly positive. So another way you could think about this is the following. So say that I tell you that I have a global surface and that Gauss theorem egregium holds, and the curvature is positive. Okay? So that is telling you that the Gauss map never peaks somehow points, right? With, I mean, counted negatively. Okay, so if I make a small picture, right, so this tells you that a situation like this is forbidden, right? Because a point like over here would be a saddle point, and for that the Gauss curvature is actually equal to something negative, okay? So one other way to see this is the following. So if you take a map from S2, if you take an immersion from S2 in Rn, okay, the degree of the Gauss map as a map from S2 to S2 is equal to 1, okay? And if the Gauss curvature is positive, this is telling you that every point is taken exactly with multiplicity 1, right? Because if you take it with multiplicity higher than 1, then you will have a point where the degree is bigger than 1. Okay, so this, of course, this is using a hell of a lot of derivatives, but you can use degree theory only for C0 maps. And so what really counts is to find a weak way of formulating this thing. Okay, anyway, so this is the upshot. Pogorelov plus theorem egregium actually does the job. So now, say that you want to prove theorem egregium for C1 2/3 plus something. Or in general for C1 alpha. Okay, so what you could actually do, you could do the following. So you take your mu, so from sigma into Rn. Well, okay, so this is somehow in R3, so this is 2-dimensional. And what you could do actually, so you could regularize U by convolution. So that's, or by whatever mechanism you want somehow. You can regularize it. Okay? Now, U epsilon actually induces a new metric. U epsilon, I mean, if U is C1, U epsilon is converging in C1. So the Gauss map is converging in C0. So the area distortion of U epsilon is converging to the area distortion of U. And now for U epsilon, you have actually Gauss theorem egregio. So the only problem is when I compute actually the curvature of G epsilon, will it converge to the curvature of G? That's absolutely not obvious, and in general, you don't expect this to be correct. Okay, so you could now make a computation. So you could look actually at the Gauss curvature or the Riemann tensor if you want. So R epsilon, or if you want, you look at this, R of G epsilon. Okay, so how does R of G epsilon looks like in coordinates? So this looks something like this. So it's going to be something like the derivative of the Christoffel symbols. And there is something complicated, which is products of Christoffel symbols with themselves. Okay? So now, Christoffel symbols are one derivatives of the metric. Right? G is one derivative of this guy. So the Christoffel symbols are two derivatives of the metric. Now you see right away why C2 is a very lucky situation. So for C2, the Christoffel symbols are converging to the Christoffel symbols, and this product converges. And this derivative is taken outside. So in the sense of distributions, it will converge as long as gamma converges. So now what I claim is actually that the following funny theorem, maybe let me scale it over here, is a funny proposition. And at first, it looks a wrong proposition. So gamma of G epsilon actually converges to gamma of G as soon as U is slightly better than 1/2. So although I'm computing second derivatives of U, actually the convergence is okay already if you're slightly better than Hölder 1/2. It's very surprising. And remember the conjecture of Gromov, which tells you that the threshold should be 1/2. So that gives you an idea why 1/2 is lucky. And when you look at this, you could actually ask why. So what is happening? So it's happening the following. So this could be the proof. So if you look at how the Christoffel symbols are computed, so gamma are quote unquote a derivative. I mean, it's something like okay, so something like G, and then here there will be derivative of things like this. I mean, it's a linear combination of these guys over here. Okay, so never mind this part. What I'm actually claiming is that this will converge, and uniformly if you are better than 1/2. So how actually it comes that the derivative of G epsilon KL is converging to the derivative of GKL uniformly when you are slightly better than Hölder 1/2. Okay, so there is a funny thing happening. So remember that I'm assuming that although my map U is not good, the background metric is good. So what I could really look at is this difference. So I take the convolution of the metric. Okay, and I look at the difference between these two operations. So here what happens is the following. So you take your surface, you make the isometric embedding, so you compute this quantity which is quadratic, and then you make a convolution. Here you make a convolution of U, and then you compute the quadratic quantity. So this is a commutator estimate. Now, if this is converging to 0, since this actually is nice and smooth, of course the convolution here of this will converge uniformly to that, and there is no problem. So the main point is in here. And what is happening is the following. So when you compute this guy over here, you will see this expression. it's an elementary computation, but it's a smart computation. What I'm saying is the following. So these are two functions which are Hölder 1/2. And if I take the product of two Hölder 1/2, I mean, if I regularize two Hölder 1/2 functions, take the product, and I subtract the regularization of the product, this quantity is converging uniformly to 0. So this is a very elementary commutator estimate. So if you have alpha and beta, which are two Hölder 1/2 plus something functions, and you take the following quantity, you take alpha beta, and you regularize by convolution, and you subtract the product of the two regularization. So this actually converging to 0 uniformly. Okay. It's a simple exercise. On the other hand, if you go back to what I told you, it's Onsager's conjecture, the proof that there is energy conservation for alpha bigger than 1/3, which was given by Konstantin ATT, it's a one-page proof, and it's based on this commutator estimate. It's exactly the same proof. Now, you might wonder, once I've done this, why I need actually, instead of 1/2, I need 2/3. So this is a bit more complicated computation. What actually happens is the following. When you look at the integral, which is defining, which is giving you the Gauss theorem in a formula, it's a bit more complicated. Instead of being the product of two functions and taking one derivative, it's the product of three functions, and you are taking two derivatives. And you want to pass into the limit for that. And there is a similar commutator estimate, which is telling you that if you have somehow a product of three, but you take two derivatives, then we will need an alpha such that alpha plus alpha plus alpha, which gives you 3 alpha, minus 2 is bigger than 0. And this gives you this alpha equal 2/3 plus epsilon. Okay, so it's only computationally slightly more challenging, but that is all that should be sent to the proof. Now, when you actually have the convergence of the Christoffel symbols, it looks like you still should be able to do something, but unfortunately, for a technical reason, the proof actually breaks down. So for 1/2, we have not been able to do anything. So it was announced actually in January that by a person I know, by a mathematician I know, that he could solve this problem for 1/2, but it turns out there is a mistake in his proof. So it seems it's still open. Okay, so now, what happens to the Nash Kuiper theorem? So why we have the other threshold, which is 1/5, which is what I'm going to explain you in the remaining, say, 20 minutes. Okay, so in order to give you an idea for this, I have to tell you how the Nash Kuiper theorem is proved. So now you remember Kuiper does it in codimension 1, and Nash does it in codimension 2. So I'm going to do like Nash. Since in codimension 1 the computations are much more complicated and they hide some of the ideas, I'm going actually to assume I am in codimension 2. Okay? So assume codimension 2. Okay, so in codimension 2, Nash does what I think it's up to date, the most unusual iteration for proving existence of a solution to a PDE. So if you're setting up an iteration for proving that there is a solution to a certain PDE, you usually linearize in some way, one way or the other, the equation, okay? And you're taking advantage of this. Nash is doing something which is completely counterintuitive. He treats the linear part as a perturbation and the quadratic part as the main thing. So what he's doing is the following. So assume you have your map V, which is going from sigma into Rn, and is short. Okay, now I look at this guy over here. Let us call it H. This will be called the metric error later. Now, H, if you are in coordinates, it's simply a symmetric matrix. So you might believe it that I can decompose it into a sum of rank 1 tensors. Okay, so I'm going to decompose it into a sum of something like deep psi k tensor deep psi k. How many do I need it? I will discuss it in a second. So this number n that you need, at least locally, should be bigger or equal than the dimension of the space of symmetric matrices. And you see why this number n times n plus 1 starts popping out. Okay, now, once I have this decomposition, I ask myself, can I perturb V to a new V1 so that when I compute the pullback of the new metric, I'm going to have the old metric plus one of these guys, which anyway are called nowadays primitive metrics. I don't know who introduced actually this terminology, probably Gromov, because Nash doesn't call it that way. Plus an error, which I have to allow myself, but the error is going to be very small. Okay, so how do I do this? Well, I fix B and N orthonormal vector fields which are also normal to the surface. And I look at a very explicit perturbation, which is of the following kind. So V1 of x is V of x plus. Okay, so let me actually, so this is not true literally the way I've written, so there is a coefficient over here, which is called AK squared. Sorry. So this is just a coefficient. Okay, so now what happens when I compute the derivative of this guy? So when I compute the derivative of this guy, I get the following formula. So I have this guy. Then when I differentiate the cosinus of the sinus, I get this lambda, which is going to be a very large number. So your perturbation is spiraling around the surface. It's oscillating very much. So this very large number cancels with the denominator over here. Okay, I believe here I have sinus, and here I have minus. Okay, then I have a lot of other stuff, right? But it's of order lambda, 1 over lambda. So for instance, one thing that I have is something like this. I have something like 1 over lambda. Then I have AK of x, and then I have a derivative of dB. And I have a lot of other terms like that. But the important point is that I always have this 1 over lambda. So if I shoot lambda very large, I can actually treat this as an error. Okay, and now if I compute the metric which would be induced by, so if I compute the metric which would be induced by this, so if I compute dV1 transpose times d1, it happens the following. So first of all, you have the quadratic parts. So this gives you this is no okay, sorry. So this gives you, so this is V1 pullback of the Euclidean metric, and this is the pullback of the Euclidean metric time by E. Okay? Then what do I have? So I have actually, when I take the transpose of this, right, so I will have the scalar product of Bx with itself, that gives me 1, and then I have deep psi 1 tensor deep psi 1. Then I have AK squared, and then I have sine squared. So I get sine squared from here, and I get cosine squared from there, which gives me 1, right? So gives me 1, and therefore I just have this guy. By the way, this should be A1. Yeah, this is A1. Sorry. It's always A1. Okay, this is precisely what I wanted. Now you see that the mixed derivatives cancel. So for instance, why this transpose times that cancels? Because n and b are orthogonal. So there is no double product from this guy. Why this one times that one cancels? Because n of x is actually orthogonal to the surface, which means that it will be in the kernel of the transpose of dv. So when I make dv transpose times this, actually it cancels, because that gives 0. So all the mixed terms cancel. And if you think about what these mixed terms are the linearization of the equation. So I've made actually the linearization of the equation equal to 0, and the quadratic term is what is giving me the perturbation that I wanted. Okay. Then of course I still have 1 over lambda, which is multiplying this massive stuff. Okay, but this is of order 1 over lambda. So here we go. I'm essentially done. What I will do is I will iterate this procedure, add the primitive metrics that I want to add, which are finitely many, and then I end up with my new isometric immersion or embedding. Depending on the starting hypothesis, I can prove actually that the perturbation is also going to be injective if my net is injective. And now I iterate this process. Of course, I cannot directly in one single shot get to this exact guy, right? So because I have the errors. Okay, but I got much closer to it. So now I get a new error, I expand it in that way, and then I keep iterating this procedure. Okay, so now you might ask, can I make this procedure quantitative? So it's very easy to prove that actually it converges in C1. It's very, very easy. Why it's very easy to prove that it converges in C1? Because if you look at the difference between these two derivatives, right? So the difference between these two derivatives is essentially the amplitude of this guy. Okay? So now forget about this one, which has modulus 1. It's the amplitude of this guy. Okay? And how big is this guy? So in this decomposition, everything is positive definite, right? So over here, everything is positive semi-definite. So each of these pieces is bounded by h. In particular, the size of this times that is bounded by the square root of h. So the amount of C1 norm that you have to add goes like the square root of the metric error. So if I make the metric error converge exponentially, the square root will be an exponential, and then I'm converging actually exponentially in the C1 norm, right? So it's very, very easy. But now what happens to the C2 norm? So you cannot do C2. And why you cannot do C2? It's because when you take a further derivative, this lambda is popping out here in front. And now you have a competing, you see, you have two competing terms. You want to shoot lambda very large, because this thing has to be small. But you want to keep lambda small if you don't want to blow up in the C2 norm, okay? And you cannot do that. Now, you cannot do that, but you could, of course, hope that, you could kind of balance the two issues. So by choosing lambda not too large, you take advantage of the fact that this guy is converging to 0, the error, and somehow you could balance between themselves and hope that you get a Hölder exponent. Okay? So now let me give you a like 2 minutes computation. It's a kind of back of the envelope computation, but it tells you why, for instance, this 1 over 3 is a special exponent in this situation, which it will tell you why this 1 over 3 is a special exponent for the Euler equations. And as far as I know, this Onsager's conjecture is derived by purely dimensional considerations on a physical system. This is the only quote-unquote mathematical explanation that I have, or that it seems to be around, for why this exponent is special. And of course, then you could argue that why we cannot reach exactly the conjecture, why we don't have 1 over 3, we have 1 over 5, and so on. These are kind of finer details in the mathematics of what we are doing, so kind of technical details, if you want, whatever the meaning of technical is. Okay, so let's say we are at a certain step in the iteration. So we have produced V. Then we will produce, so in a sense, this V1 is not really the real next guy, because I've only added one primitive metric, right? So in some sense, I should call this V11. And then there will be a V12, a V13, and then when I've done all the steps, there is really V1. Okay, so I have a V, V1, then I generate V2, and so on. So I generate VQ. Okay, and each time I generate VQ, I have a metric error. So I know that G minus VQ E will have a certain size. So let us say that the C0 norm of this guy is delta Q. Okay? So now I know that VQ plus 1 minus VQ in C0. So I have to add something which is of the size of delta Q to the power 1/2. That's what I told you. So the next guy differs, in C1, so the derivatives. So the derivatives of the two guys differ by the square root of the metric error, which I had. Okay? So this was this consideration over here. Okay, on the other hand, you could imagine that your second derivative is going like a constant, then you will have delta Q to the 1/2, and then you will have this lambda. Okay, so let us call it lambda Q plus 1. So lambda Q plus 1 is the frequency of the oscillations of the spirals at the next stage of the iteration, is this lambda. Okay? Okay, sorry, so this comes from the previous guy. Right. Okay, so now what do I want? So I want the next metric to have a size which is delta Q plus 1. So I want this condition. Okay, remember in this expansion, right, I have an error term. This is the error term. One of the possible error terms. So what I want is therefore this guy, this error term, to be less or equal than this delta Q plus 1, right? So which is the next, much smaller, but say smaller by a certain fraction, 1/10 times that. Okay, so let us look at this then. Okay, so that error is going to be equal to, so delta Q plus 1 is the next thing that I want to add to the 1/2. Delta Q to the 1/2 divided by this lambda Q plus 1. Okay, and then I have the previous guy, which is delta Q minus 1. Okay, so here there's actually a mistake. So let me think about it. So here I'm adding, right. Here it's actually like that. Right, because it comes from the previous iteration. And here I will have lambda Q to the power 1/2. Okay, so the inequality that I want is the following. So delta Q to the power 1/2. Okay, so here there is also a 1/2. Delta Q minus 1 to the power 1/2. Lambda Q to the power 1/2 divided by lambda Q plus 1. Okay, so this has to be less or equal than delta Q plus 1. Okay, so this is the minimal requirement on my iteration to make things work. And now you can play the following game. So let's say that you insert an exponential ansatz. So let's say that you insert that delta Q is going down like 2 to the minus Q. Okay, and let's say that you insert that lambda Q is blowing up like 2 to some power beta times Q. Okay, so you can compute the minimal beta, which gives you hope for this inequality to be correct. And then you go back to this thing over here, and you make the following interpolation estimates. So if I want to compute the C alpha, C0 alpha norm of this guy, okay, then I have interpolation, and I know that this is going to be less or equal, and I will have the C0 norm to the power 1 minus alpha times the C2 norm. Okay, now the C2 norm will be blowing up by this rule, okay, but the C1 norm is but the C1 norm is actually converging by this rule. So if you make your computation correctly, you will essentially discover here that there's going to be something like 2 to the minus Q plus some other function of beta times Q. Okay, so you compute this function of beta, and of course you want this function of beta to be less than 1, so that this guy is converging. So this is a function of beta and alpha, sorry. So you have an optimal smallest beta that you have over here, and then you can compute what is the best alpha that you can put over there. And the best alpha is actually 1 over 3. Okay, so this is all very simple computations. It does not tell you why actually we cannot do this 1 over 3. Well, there is one aspect which I am actually forgetting, and the aspect is the following. At each stage, I'm not adding only one primitive metric, but I have to add many. So this would be actually the exponent that I reach if I had my metric error as a decomposition with one primitive metric. Okay? So remember that I have to put many. Okay? So at the stage, I don't only have to put this lambda Q plus 1, but then I have to do it a second time, a third time, a fourth time, and then only at the end of 4 or 5 of these iterations, I actually look back and I can compute the next error, and I can compute the next increase of the C2 norm. Okay? So this would be working for curves, for instance, but not for surfaces. Okay? So now the point is that, so let me make the following remarks. So, first remark. So more primitive metrics to add. Worse Hölder constant. And if the number of primitive metrics to add is n, the Hölder constant becomes 1 divided by 1 plus 2 big N. Okay? So now this primitive matrix, if you remember, it's a decomposition of a symmetric tensor in rank 1 tensors, and in general, you need at least as many as the dimension of the space of symmetric matrices, which gave you this n equal to n times n plus 1 divided by 2. So this gives you Borisov exponent in the situation where you have one single patch. But if your manifold is more complicated, then for instance, if it is a sphere, then I need 2 patches, and then I need to be more careful. So it essentially, the real number when there is topology depends on the number of patches that I can put independently. Okay, so it's a combinatorial topological reason to see that with topology, you can actually do this n at least is good. Okay. Second comment, or third comment. So there's a lot of analysis that I am actually disregarding. So a lot of troubles. And the troubles are in the following. So if I want this iteration to close, right, I'm only taking into account of the C2 norm of the map at each stage. But I've showed you the computation for the metric error, but then I have to prove iteratively that my C2 estimate holds. And when I compute the C2 norms, I will call C3 norms of the previous map. Then I have to take into account those ones. But then they will call the C4 norms. So then I have to keep track of all of them. And that's the reason why Borisov uses analytic metrics. It's because he computes everything. And it becomes a little bit like KAM theory or hard implicit function theorem. What you can actually do, and what we do in our proof, is to introduce a regularization step in such a way that we do not have to call back previous norms, very high CK norms in our iteration. Okay, so a lot of troubles. Here there is a loss of derivative. Okay, so why? So of course this gives you now an idea why you get 1/7. So without topology and n equal 2, then you get big N equal 3, and you get this guy equal to 1/7. So why 1/5? In our latest theorem. So the reason is the following: is remember I want to decompose my metric error into sum of rank 1 tensors. So take your metric error H. So this is actually a metric. So I can change coordinates conformally and make it diagonal in some system of coordinates. Right? So if I change conformally and I put it in this way, then my decomposition as a sum of rank 1 tensors actually needs only 2. And if it needs only 2, this number becomes 1 plus 4 and becomes 1/5. Okay, so this is true, but the proof is much more complicated than one would imagine, and the reason is the following. So it would be really literally that easy if along the iteration the conformal change of coordinates would get uniform estimates. But unfortunately it's not the case. So unfortunately the estimates are blowing up, they are degenerating. And the reason is essentially the following. So I have to normalize this metric error, right? So in C0. So if I had estimates for the conformal change of coordinates in C0, so C0 metric gives me a C1 conformal change of coordinates, everything would go through very smoothly. But I don't have that. I have to go to Hölder estimates actually, because the endpoints estimates for elliptic PDEs fail. Okay, then things start being pretty bad because the C alpha norm of the H normalized by the C0 norm actually goes up. It's not even clear at the first instance that this estimate, this inductive procedure would close because the estimates are bad. So it turns out that if instead of making this going down exponentially, I make it going down doubly exponentially, so slightly more, then I can take advantage of the fact that this is converging faster, and I can still close the estimates. And that's why the paper is actually much more difficult. So difficulties because we lack C1 estimates, and we have to go to C1 alpha estimates, or C1, let's say, mu estimates. Okay, and then it becomes involved and much more hard analysis than actually this other one is. Okay, so that's all I wanted to tell you.
Are there any questions?
So if you're embedding it very high codimension, it seems you can get from VK to VK plus 1 in just one step by doing spiralings in a bunch of pairs of directions.
Right.
So you can get 1/3 in that.
Right, you can get 1/3. Actually, you can do even better. So there is there was a paper in the 70s by a student of Hermander, Kellen. So a naive thing is if you have high enough codimension, you can do 1/3. Okay, that's absolutely clear from the way we were making the iteration. But then if you add even more codimension, you can actually kill many more of the error terms. And you can get to 1/2. But you can actually get almost to C11, because if you have really a lot of codimension, you can start killing essentially, you could in a sense make some sort of formal expansion in lambda, and you can really kill it by an algebraic trick, essentially all first terms in the Taylor expansion. Okay, so you can get almost to C11.
How does this codimension grow with?
So the codimension grows. So to get to C11 minus epsilon, there is a threshold. So it's actually that's a nice picture if you combine the hard implicit function theorem, so the smooth embeddings and the non-smooth embeddings. The C1 alpha. So there is a nice picture which tells you that. So if this is alpha, so you have something like this up to here. So this would be like C2. So this is C0, and then it goes like that. And okay, so when there is, at a certain point, of course, when the dimension is really large, there is the hard implicit function theorem that kicks in, and you can embed even in C3. Okay, and funny enough, this infinitesimal spot there, it's actually open. So people knows how to embed C2 alpha, C below you have the C1 alpha, but C2 is an open problem. And it's actually open since the paper of Nash. So Nash is already posting the problem that he cannot embed the C2 metric with a C2 immersion or embedding.
What happens when you embed into Lorentzian manifold? It should be much easier, right?
What happens? I didn't think about this actually.
How about local isometric embedding?
Okay, so if you want, if you put a lot of assumptions, if you put real analytic metrics, then it is this classical work by Cartan and Janet and Burstein that the dimension which looks like the real dimension is the correct one. But so if you're going to look at C infinity, that is for instance wrong. So there is this counterexample by Nadirashvili that is a metric on 2 dimensions which cannot be locally embedded in R3.
Are you sure that? I thought there was some mistake on the counterexample.
There is a mistake. Okay, so I didn't check the. I didn't check the proof. I'm only telling you what I got from other surveys. So I you have to be honest. I didn't check the proof. But as far as I know, it's okay. So if that counterexample does not work, then it's completely open somehow. Even for
not completely. There's non-negative characters. She has improved that.
Yeah. So if you
sure.
No. There are of course very good results if you impose something on the curvature. But if the thing is general, then and if you leave, I think the 2-dimensional work, then it starts being.
So this kind of argument can I have for local?
Okay, sure. This of course will give you C1 immersions, but they are not regular enough for being nice, right? So sure, this kind of arguments are always going to give you in codimension 1 the immersion of whatever metric, but then the Hölder exponent will certainly be, well, certainly you cannot get C2, for a very obvious reason that the estimates will blow up.
Are there any more questions? If not, let's thank the speaker again.